Today's topic is BFGS, or the Brouillon-Fletcher-Goldfarb-Shannon algorithm, named after the four people who discovered it simultaneously, but separately. And so it was named after all of them. So let's just go through it. This is just a little bit of a preface about what we're talking about today. So we're talking about optimization, and it's essentially a lot of numerical linear algebra. So most of you, I'm assuming, are computer scientists or CS majors. This may feel a little bit unnatural at first. I try to make it as understandable as possible, but understand that even though this is computer science, it tends to lean a lot more towards the side of linear algebra. I expect you to know multivariate calculus and at least have a solid foundation in linear algebra. If you don't, I've again tried to make things as nice as possible, but if I tell you the inverse of a matrix and you don't know what that is, you might struggle with part of the presentation, mostly the proof parts towards the end. Like the derivation. Yes.
Are these like also available somewhere on Discord?
I will post it afterwards on Discord and the recording. The quality of the recording is not guaranteed though. So, and again, like, if you don't understand something, ask me. Like, this is actually a pretty complex topic. It is covered in a grad level class, CS 520. So it is definitely more advanced than the typical topics you'll see, but it's very important in optimization. And even then afterwards in machine learning, so I'll do a future presentation about optimizers, and a lot of them are derived from these ideas. All right, so the main idea we're going to talk about today is how do we find the local minima of a function? And here, when I mean this, I mean like we're going to have some smooth function, as many different, we can differentiate it as many times as we'd like without problems numerically. Actually, in practice, you might know this in computer science, like you'll never reach exactly, for example, 0. You'll almost always be a little bit off. So in practice, we're almost never going to have, cases like absolute value of x is non-differentiable because we're never really going to have 0. And so the goal is going to be to find local minimas. Why do I say local minimas? Because finding a global minima is actually NP hard. So it's actually kind of impossible, mostly for continuous functions. So we're just going to consider local minimas of smooth functions, continuous, differentiable, like this one. This is the Himmel-Blow function, which is one of the very common examples in computer science for optimization. It has 4 local minimas. I'll let you find, one of them is very obvious. I'll let you find the others. If you want, like numerically, it's a little bit annoying. So that's going to be our goal today, is how do we get to the local minima? And that's obviously very common in computer science. Like machine learning is literally how do you optimize a model, like a neural network, and you find the minimal loss for the given data set. And so that's really going to be our first problem. And I'm assuming most of you know about gradient descent. So let's just briefly talk about it. The gradient is the direction of steepest descent. And that means that the opposite is going to be the steepest descent. Again, we're trying to find a minima, so we want to go descent. Numerically, that's written as this. So x, the new x, so your new state, like your new position, is the previous position minus some alpha, which is, in this case, your learning rate in computer science, times the gradient. And so this will just keep getting you closer and closer to your final solution. And if you have a small enough learning rate, you'll actually converge. There's a few details I'm going over, but essentially you're guaranteed to converge linearly with gradient descent, which is great. And this is how it looks like. Let me just push the sharing screen thing. So you see you have your point in red, and you have a little arrow which represents the direction. And so you take a step in that direction until you get to the minima. Great. Everybody understand this? No questions, right? I mean, if you do, please do let me know. But all right, let's talk about Newton's method now. And the basic of Newton method is gradient descent is one-dimensional. We're only looking at first order approximation of a Taylor series. You're only looking at f prime, like the first derivative. Now we're going to look at the second derivative. The idea behind this is as you get more and more derivatives in your Taylor series, you get a better and better approximation of the function. Eventually, when you reach infinity, you actually get your function, but we're not going to do that because infinity is hard to compute. And we're actually going to stay at 2 for now because for the rest of this presentation is going to be about second order approximations, and I'll explain a little bit more about that later. And we're just going to talk about it in single dimension for now because that's where intuition is very strong and it's easy to understand. So this is your Taylor approximation, and trivially you can minimize it by setting the derivative at 0, and you have a step size, right? Because the step size tells you how much to move in, like to move from f of x k. So great, very easy. Like you'll go towards a direction where f prime is 0. So now this is your update, right? Like you wanted f of xk plus epsilon, and now you just plug in your epsilon. And you must have f prime prime of x to be strictly positive. Again, I mentioned like we're going towards f prime is 0, but you might know that this could be a maximum, a minimum, or a saddle point. Well, in one dimension, we don't have saddle points. We just have a flat area. But like you would typically, for most of the function are smooth and like infinitely differentiable, we would not want to have equal to 0 because that would mean, you just have a line and you can do other stuff for lines. It's a lot more trivial for lines, it's linear programming. So you would never see that, but you just need to know that you're going towards a local minima, right? Do all of those cases make sense, everybody? Yeah. And like this is what we're talking about in single dimension. Now we're going to talk about it in multiple dimensions. So here you're going to see like all of the ideas of, f prime, which is your first derivative. That's a gradient. F prime prime, so that's your second derivative. That's the Hessian. This is hopefully mostly review, but if you did multivariate calculus, and sorry about that. And you should see right here your x of k. This is a vector of variables, so this indicates like a current state. So, if you're in 2 dimensions, that could be 4, -4. If you're in 3 dimensions, you would have x1, x2, x3, like, 0, 0, 1, something like that. This is just a linear algebra way of representing this, instead of having the vector every single time, because then things get a little complicated. Does that all make sense to everybody? Like both Newton's method in a single direction and in multiple directions. No confusion? Perfect. So the new update system is this. What do we observe? Well, first thing is you don't have a learning rate, right? You just take the step towards whichever place is the minimizer of the quadratic approximation. This is actually pretty nice, right? You don't have to optimize a hyperparameter or do some sort of search to find the best learning rate. Like, great. The second thing is you're doing a quadratic approximation. This is actually pretty important because if you have a fixed learning rate, you can't easily adapt to different axes. For example, if in one axis you descend very, very slowly, then you would want to take a very big step. But if you descend very, very quickly, then you want to take a small step. And actually, in regular gradient descent, you'll only go towards the direction of the greatest descent, right? But that means you're not easily optimizing over the second axis, which is also very important. And so here we are actually doing both, right? Because quadratic takes both axes into consideration. Great. I'm not going to prove this, but I think you can probably believe me that when I say this has quadratic convergence under the ideal situation, which here says like you can actually do this. Well, I'll talk about what is ideal in just a second, but linear convergence for gradient descent. Does everybody believe me when I say this is going to be a lot faster? Because we have a significantly better approximate of our function. And we always take like the quote unquote best step for quadratic optimization, for quadratic approximation of our function. Yes. I will get into that in just a second. But yes, you are right. So this is kind of how it looks like in multiple dimensions. So, this is the same point as we had before. I'm going to use this -4, 4, or 4, -4. This is the x-axis. And this is your quadratic. So you have a quadratic approximation of the function at a given point, and you find the minimum, which is here, the little blue point, and you can see that is actually really close to the minima, right? There's 4 minimas, one here, one here, one here, and one here. And so here we're actually getting really close very quickly. Pretty nice, right? And again, like this is the visual that I want. Actually, this is a visual that's really important. I want you to always have this in your mind for second degree optimization, which is we're going to be looking at the quadratic approximation. This is in 3D, so it's really nice. We're going to talk about n dimensions where this makes 0 sense to try to draw out. So, but try to think of it this way, right? Instead of just one line, here you're taking a quadratic approximation and you're going towards the minimum of it. Now let's get to your point. Why do we not always do this? The first one is going to be convexity. So, how I mentioned, like, it would be nice if we had a second degree, like a second derivative that's always going to be positive. That's effectively convexity in this context, because if it's negative, so if our Hessian is negative, then we're going to go towards a maxima and not a minima. That's a little bit counterproductive. And we could also be going towards a saddle point in multiple dimensions, which is obviously quite bad because then you get stuck at a non-optimal point. There's some easy fixes to those, which is you combine it with gradient descent, but it's still not ideal, right? Because then you have to decide how much gradient descent you want. You also know that the Hessian must be positive definite then. Positive definite is going to come up again. Essentially, you say like you have a matrix for any 2 vectors that are non-zero, this must be greater than 0. This is positive definite. Positive semi-definite is if it was greater than or equal to 0. But we don't want saddle points, so it's greater than 0. Does that seem good to everybody? I know most people might not have heard of this term in linear algebra, that's why I'm bringing it up. Then to your point, it's incredibly expensive to compute. Gradient descent is a very simple linear term computation, right? Like the more dimensions you have, the more gradients you have, like the more derivatives you have to compute your gradient. That's pretty easy to do. So if you do k steps of gradient descent, you do k times n, pretty trivial. Here we have to compute a Hessian, which is a 2D computation, and I separated them, by the way, because computing the Hessian is typically the most expensive part, or one of the most expensive parts. Simply put, you have to find like the second gradient of your function at n squared places. Computing gradients is expensive. So already n squared, that's probably too much for us to do at every step. The second problem is we have to inverse the Hessian. If you recall, this is what we have. So we have h of x of negative to the power -1. This is not a power. This is inverse, which is essentially the same thing as, dividing by in linear algebra. So we have to do an inverse of a Hessian. Inversing is big O of n cubed. Everybody believes me when I say this, right? Both of those operations are very expensive. The Hessian is actually symmetric across the center. So you might have learned this in multivariate or like the diagonal. So you only have to compute n times n plus 1 divided by 2 values, which is a little better, but that's where the big O of n squared comes from. And still like the n cube inversion, so pretty terrible. And so if you think about it in practice, the memory overhead and the computational overhead is far, far worse than computing fewer iterations. And the time that it takes you to do this for, large N, you would already be done with gradient descent. Even if it takes you 1 million or 10 million gradient descent steps, it's going to be faster than computing this just for one iteration. So, pretty good for gradient descent, pretty bad for Newton. And so we're going to talk about ways to fix this, and those are called quasi-Newton methods. We're getting close towards the end, but it's a little tricky. You can see like we're going from 14 to 23, and most of this is going to be math. Alrighty, so quasi-Newton method. Instead of actually computing the Hessian, our entire goal now is going to create a new matrix B that behaves like the Hessian. I'm not saying approximates because it is not an approximation. It only behaves like it. Some people do erroneously say it's an approximation. It is not, but it behaves very similarly to it. So it has very similar values. But in some very specific cases, it will not be like the actual Hessian. And there's one condition we always want to uphold, which is this one. It's a secant condition. Essentially, you're saying that you want to be able to approximate the second degree derivative, whatever that means, quote unquote, like whatever the second derivative means at a specific point using B. And so the right-hand side, you see that's the difference in gradients. The left-hand side is going to be the difference in points. So if you're thinking about it in terms of, rise over, like rise over run, I think is the terminology you learn in grade school, you'll see like that's just a very simple approximation of the second degree derivative. So we're just going to call that the secant condition, and we're going to say, you should always be like this. You should always approximate, like essentially be a good approximate of the second derivative. Again, whatever that truly means, but does that kind of make sense to everybody intuitively? And so you can actually see this just as a Taylor approximation of the gradient, right? Like this is what you're trying to approximate, which is the new gradient, and that'll be like the first order derivative, the change, and because this is what we compute when we do I think this no, actually I think this is correct. I might have a +1 extra in here. I might have a +1. I don't think this is incorrect, but that might be slight. I can double check this, but I believe this is correct. So essentially, this is your Taylor approximation with the true Hessian. And so your true Hessian times this is approximately like your true Hessian times the difference in x's or the difference of states is approximately the difference in derivatives, but we're going to set that as a pure equality for our new quasi-Newton matrix B. Does that seem reasonable to everybody when I say this? Yes. Here, I'm not even talking about the actual Hessian. I'm talking about, so here we have the Hessian, but we're going to talk about B, which is a new matrix, which behaves like the Hessian. So we're going to try to use this new matrix B as if it was the Hessian. It's not the Hessian, but it's still like big O of n squared in memory. It's still, going to be like a symmetric matrix. So it's very similar to the Hessian. We're never going to actually compute, well, I'll get to the actual Hessian later on, but for now we're going to say we don't compute the Hessian. We just have B, and we're going to try to see how can we update B over time so it's always similar to the Hessian. It always behaves like the Hessian. So at every iteration of the quasi-Newton steps, we're going to update what B is. Alrighty, did that make sense? Yes.
Yeah, just making sure about like that thing about the x to the k+1. Wouldn't it make sense if it's f to the x f of x base k because you're trying to do an approximation based off the over.
Sorry.
About f of x to k+1, right? Shouldn't that
This.
be of x k?
Here we're doing the Taylor approximation of this term.
Yeah, based on the previous f of x k.
Yes, so it's
Yeah,
this.
yeah. So like, you were saying that, f of x k plus one was like wrong or something.
I'm not quite sure. I believe this is correct though, because you're doing the approximation about this, like this value.
Oh,
Let me just, I can double check this. Give me 1 second, because I pulled this from, I pulled this, from, how's it called? From like my sources. So I can double check that right now. Um, but I believe it is correct. Like that actually doesn't really matter all that much. Okay, this f of xk, not x. Okay, this is actually slightly wrong. I should say like about the gradient of f of xk. So this is actually slightly wrong. So disregard this particular term. This should be f of gradient of f of xk. You're correct. Does that make sense? Like, yeah. Sorry about that. I made this today and yesterday when I was really tired, and this kind of slipped through the crack. Um, I wrote all the math I wrote by hand again, so took a while. And I made some minor mistakes. Yeah. So this should be the gradient. Very good catch. Yeah, this should be. That's why I was a bit confused, like why there's a plus sign. Yeah. So you're just doing like about the previous gradient, and you're doing a new approximation from that. That makes sense to everybody? Thank you for that. Um. Alrighty, so let's define the following just so the rest of the math looks a little bit nicer. Um, delta xk is going to be the difference between your xk's. Yk is going to be the difference between the gradients. Does that make sense to everybody? Like that's notation that should be very clear. Like you now I'm only going to talk about YKs and delta XKs for most of the rest of the presentation. So hopefully this is very clear. Delta XK, what is the change between your current point? Wait, this should be X of K. God damn it. I made some changes. Okay, this should be X of K. Sorry about that. Yeah, this should be X of K. Sorry about that. I will fix those mistakes before sending the PDF. Um, and so, but regardless, like you get what I mean, right? Like this is the difference between your old point and your new point, and y of k is going to be the difference between the old gradient and the new gradient. Um, and so your secant condition is going to be like your new b, like your new Hessian function that or matrix that behaves like the Hessian. When you update it, should follow the secant condition, which we've defined right before. Here we're just rewriting it slightly differently. And you can actually see, like, you don't know what the delta of xk could be, right? It could be anything. So you know that for this to be positive definite, you can just have the transpose of the xk before. And so you know your bk plus 1 is going to be positive definite if this happens. This is just an incidental but important idea, right? Like this is how you can show that you need to be positive definite to hold the secant condition. Alrighty. Okay, perfect. So let's just go back to one dimensions temporarily just to kind of explain how this goes. Again, because one dimension is very nice, very intuitive. 2D kind of makes sense. 3D a little harder, and afterwards it's impossible. So then we just talk about general cases. But a single dimension is very nice. So we go back, to that's essentially the secant condition, right? We rewrite this back into first dimension. Um, and you know that this implies convexity because this is essentially your approximation of the Hessian. And so it has to be positive if you want to be convex. Very nice. And so the updates, if you plug this back into the very original idea, which was, Newton's method. I can go all the way back. Like this is Newton's method. So Plugging it back, you take the inverse of this, which is 1 divided by that in one dimension. This is what you get for your updates. This is really nice. This is a quasi-Newton method called the secant method. It's wonderful. Do you guys have any questions? And you should have. You should have at least one question for me. Okay, we don't. I'll give the question then. But there should be something glaring, or like a glaring thought in your mind right now. Why can't you do this in multivariate, like variate cases, right? Like this is so trivial, so nice. Why can't you do it? The answer is just because one dimension is super nice, but B has n squared number of components. If you remember, right? It's n times n plus 1 divided by 2. But you only have n equations, right? The size of these vectors, xk, like delta xk and yk, they only have n dimensions. So you're trying to solve for n squared, well, n times n plus 1 divided by 2 variables with only n equations. That's actually a bit impossible. Like, it is just impossible. You can't actually solve for it, so tough luck. In one dimension, it actually works out quite nicely because you get n times 1 plus 1 divided by 2, so, well, n is 1, so n, 1 times 2 divided by 2, that's just 1. And so here you have like one equation. So one component, one equation gets you secant method. Everything else, it stops working. That's a shame. Let's keep looking. So now we're going to talk about BFGS, which is the reason why most of you guys came today and the main topic of the presentation, but everything before was just built up to try to get the foundations of why BFGS. Because BFGS in of itself is a little bit easy or could be covered in like 5-10 minutes on its own, but like you need to truly understand why it happens. Again, we want BFK to be symmetric, like the new BFK, so BFK plus 1, to be symmetric. We want it to be like the Hessian in that aspect. That's the first condition. Second condition is it must be positive definite. Again, because we always want to go for minimas. And so if we're ever at, if it's ever 0 or positive or negative, they're going to reach a saddle point or a maximum. And so this is actually a little different than the Hessian. So that's your second condition, and that's why I'm saying it behaves like the Hessian, but it's not an approximation of the Hessian, because it's positive definite, and the Hessian isn't necessarily positive definite. Third condition is whenever you update this matrix, it must be reasonably close to your previous matrix. This is to prevent instability and like, if you're taking some step, you shouldn't expect your Hessian to move that drastically in most cases. Right? So we want B of k plus 1 to be reasonably close to the old B of k. Do those requirements make a lot of sense intuitively to everybody? Because they're pretty important and they're going to be the basis of BFGS. We can put them together. And so essentially you're trying to minimize the difference with the Frobenius norm with two requirements. The first one is it's symmetric. So the transpose is equal to the original matrix. And you have the positive definite, which is the secant condition, essentially. Right? Everybody good with that? So this ensures that we're trying to be as close as possible to the old B. This ensures that we're going to be symmetric, and this is for positive definitiveness. And to also ensure that we're close to the Hessian. So it does serve two purposes. That should all make sense, right? Okay. Also, the choice of using Frobenius norm for closeness is arbitrary, but it is actually, if you do the full proof, I'm omitting a few tiny parts later on, and I'll explain when I do them. But this does have impact later on, but Frobenius norm is very common in optimization. It's used a lot in statistics as well, so very important norm anyways. Very tiny correction, and it's going to become more important later, but we actually don't want H. We want the inverse of H. do you understand why we want the inverse of H? Do you remember what the Newton's method was? Yes.
It's kind of like the gradient over that Hessian, or it's like inverse of Hessian times the gradient.
Exactly, it's inverse of the Hessian times the gradient, or times, yeah, times the gradient. We can go right back to the very beginning. Like this was the one dimension, and this was n dimension, so you have gradient times the inverse of the Hessian at x of k. So, oh, going too far. A little preview, I guess. We're going to essentially solve this. This is what I'm saying, like, I'm going to skip a few steps because the proof is very long and complicated and tedious and would probably get you all lost in the time that we have. So I'm skipping over some details, but if you read the proofs, like in the textbooks and sources, you can actually see how they do it. But essentially, that's what we're going to try to solve, is how do we get b of k plus 1 given b of k, changing x, delta xk, and yk. So we're going to first define, and this is actually one of the main ideas of BFGS, is we're going to update b of k plus 1 with two new matrices. Each of those matrices have to be rank 1 matrices. The result of this action means that we update b of k plus 1 in only 2 ranks out of n ranks. So we're actually changing very little. We're changing the minimum possible of b of k plus 1. Like, we could change a little bit less, but we don't, because then we can't, there is no, it's actually impossible to do it with just 1 rank because of degrees of freedom. So we have to do 2 ranks. So we have to do 2 rank 1 matrices to update b of k plus 1. So that's going to be the very basic of what we're going to be doing. And since both of them are rank 1, you can actually make them outer products, because the outer product results in a rank 1 matrix that's symmetric. And so then you just multiply them by scalar, and this should have a b of k. Sorry about that. Yeah, sorry about that. Again, like, I'm sorry, there's a few minor mistakes. I had to type it all by hand, so I'll make sure to correct that by the time I upload the slides, but you should be able to infer, right, b of k plus u plus v. Each of those are symmetric. That's great. It means that b of k plus 1 is also symmetric. We're only changing 2 ranks because each of those are rank 1 matrices. Again, great. It means we're changing very little from the original b of k. So we're going to continue remaining symmetric, and we're going to continue being close. Two of the 3 requirements are already accomplished. Isn't that great? And now let's just plug into the second condition, which will allow us to get and to prove positive definitiveness. So this is what you get, right? Like, you just upload, like, directly push in with b of k plus 1, which is b of k plus u plus v. And so that's, again, just an outright simplification, and that's equal to y of k. Make sense, everybody? All right. The natural choice for u and v is y of k and b of delta xk. This is a little weird, but like, those are the only vector, like, those are the 2 vectors you actually have access to, right? You currently have 2 vectors. You have y of k, and this is another vector. So you have 2 vectors. And in a way, you can think of it like, if I'm saying it is a natural choice, it's because it depends on your intuition, but you can see how y of k is what you're trying to be, right? You're trying to make b of k times delta xk into y of k. That's your goal. And b of k times delta xk, that's what you used to be. So you're trying to move away from what you used to be, right? You're trying to move away from what you used to be, and you're trying to move towards your goal. So that's a little bit of like the intuition why it's natural. But really it's because it makes the proofs work out nicely. But like, that's the intuition behind why it works. So you're trying to update towards your goal, remove from what you don't want. Makes sense. I'm seeing some nods, so I'll assume this makes sense to everybody, right? and this is kind of what I'm saying, like it's going to get more and more complicated in the linear algebra side. Um, so this is our new update in terms of what, like how we change it, right? We just updated it to, we just plugged in what we just had before with u and v, and so this is what you get, which again, this is all just b of k plus 1, right? Times delta xk. And so how do we make this true, right? We have this a term and this b term, and it's all very nasty. Well, we can just make this 0 equal to 0. So 1 minus 1 and 1 plus negative 1. So this is 1 divided by just this term and 1 divided by just this term. There might be another minor mistake. Is there a mistake? Okay, I might have made a minor mistake, I think, in here. Yeah, I think there's an extra delta x. Yeah, there's an extra delta x transpose right here. Sorry about that. Again, I'll promise I'll try to fix as many of the mistakes before I upload them. I'll make it, this is a little bit unacceptable on my end. I'm really sorry about that. This was just a delta xk, which got taken out when we factored it, but the rest of this is correct. And so what you can see here actually is a is a positive number, right? It's yk times delta xk. And this is times u. So this is going to be a positive number times our goal, which is y of k. This is good. What about b? Well, b, we know this is a positive because b of k, we're assuming is positive definite. Like the previous b was also already positive definite, so we're going to stay being positive definite. So this is positive. So this entire thing is negative. So what does that mean about v, which is what we're trying to get away from? It means v is going to be multiplied by negative, so we're going to move away from v, like from what we don't want, the b of k times delta xk. That's convenient, isn't it? Like we're, again, like we're going towards what we want and we're stepping away from what we don't want. And so this is BFGS, if the screen sharing gets away. This is BFGS. When people mention BFGS, it's this formula. We're not done. Can anyone tell me why we're not done? I brought it up a little bit earlier before. Think about what our true goal is when we do Newton method. Are we looking for the Hessian or the inverse? Yes. What do we have here? We just have the like the b of xk, right? B of k plus 1, not b of k plus 1 times to the power of negative 1. We're still not there. One more step. So this is, I'm going to gloss over a little bit of the details here just because it's annoying and it's annoying algebra, but there's a very good formula, Woodbury formula. It allows you to take the inverse of an addition. You can actually set each part of the previous formula into individual matrices and vectors. And so you said U, C, V, and A is just B of K. This comes directly from just moving this this term before and then separating it into those three new terms. So that's why I'm not going too much into depth. I'm just letting you know we can actually convert the regular BFGS formula into a format that works with Woodbury. And so here we just get the inverse after some derivation. Again, I'm glossing over. So this is what you're really computing in practice. Because now you don't even need to do an inverse. You're just computing the update of the inverse. Isn't that great? And let's just make sure that this is positive definite, right? So we know that this is already positive definite, and we're multiplying it by two other positive definite terms, or two vectors, and we have a positive definite, so positive definite times two vectors is going to stay positive definite. Good. The last term is the only thing that could change the sign, and we've already established by the secant method that this is going to be positive, right? That's what the secant method mentioned way back then, right here, right? That's why I said like the secant method allows you to have greater than 0 because you have like positive definiteness. Alrighty. Yeah, sorry. Let me just make sure we're not running out of time. Okay, so this last term is going to define it. So if we have Z transpose times B of K plus 1 times Z, that's what we're trying to make sure is positive definite. We would just have like ZT, like Z transpose here and Z. Well, Z transpose times delta XK or delta XK transpose times Z, those are the same sum, or like the same value. So we're just going to set them as a square. And again, this is positive. This has a square, this is a quadratic, this is greater than or equal to 0, and in practice you would want this to always be greater than 0, but because you know the first term is greater than 0, because of positive definiteness, it doesn't matter what the last term is as long as it's not negative, and we just showed it's not. Great. What's the last thing? B of 0. What do you start your original B as? You can begin with either the true Hessian, so you only compute it once. That's when I said we're only going to compute the Hessian once. But we only want to do that if the true Hessian is actually positive definite, which isn't a guarantee. Otherwise, we just use the identity matrix. And if we use the identity matrix, can anyone know what we're going to do at our first step?
I'm not sure.
So the very first step, yeah.
No, I was just.
I called on you. You have to answer now. Give a shot.
Okay, sure. Do you have to, considering these other like parts of the equation, do you like try adding onto that, like onto the identity matrix to somehow like dope it with values that you can use to eventually ghost me?
Well, every time you do an iteration, you update the B matrix. This is the update. So you have your previous B, and you update it with the change in gradients, which is the Y, and the change in X, which is delta X. So that's how you update your the new matrix that behaves like the Hessian. But now what I'm saying, like for the very first Hessian, B of 0, what happens if it's the identity matrix? Maybe it can help if I go all the way back to Newton's method. And you see what will happen if we have just the identity matrix. What? Yes, what's that called?
Just like the opposite of the gradient?
Yeah, just gradient descent. So very first step is gradient descent if we do with the identity matrix. And then, as you mentioned, it's going to be an iterative method where we're going to build up the approximate of the Hessian over time. We can't solve for the Hessian because I mentioned we don't have enough equations, but we build it up over time. And so let's talk a little bit about what happens when you code it up. How do you use this in practice? The answer is you don't have to. People already did it. Like, don't shoot yourself in the foot. There's also a lot of minor modifications that people have made to BFGS, but I'm just going to show like with the main one, just in Python with SciPy. So the Hamel-Blow function is the one I showed before, again with x is equal to 4 and y is negative 4. And so you start with 4, negative 4. The z value is 170. And this is what happens with various gradient descents. As you can see, like the smaller your gradient descent step is, the more iterations you take. That should make a lot of sense. But you also do need a smaller and smaller gradient descent to make sure you actually do converge. That's a necessity for gradient descent. So you would need to show after some point, like, if your learning rate was like 1, why it would work. But most people would use like 0.01 or 0.001 or 0.001, right? BFGS, you don't need to set a learning rate. Same thing with Newton's method. So BFGS, you need 11 iterations, Newton 7. 11 to 343. That's a pretty big step up, knowing that you did not have to compute any second derivative except maybe for the first step. or if you use raw Newton, I mean, this is going to be a lot slower, but it's only 7 iterations. And this is a Himmelblow function, which is a relatively nice function for gradient descent. I can give you examples where gradient descent will simply not converge or will not be able to work just because the values are either way too big or the descent is way too slow. Like, an example would be like 1 over x. Like if you want to reach something that's really close to 0, which is going to be like some extreme value of x, depending on your floating point number, like gradient descent will take a really long time to get to a large value of x. BFGS and Newton will get there way faster. Yes.
So I'm assuming, I guess, each iteration, like, for different methods, the iterations take different amounts of time.
Yes. So BFGS, you still have a big O of n squared in the memory footprint. And you still technically need like big O of n squared additions in your matrix, but that's really quick. But you don't need the inversion, right? You don't need big O of n cubed. That's amazing. You already took it by 1 degree off, but you also converge way faster and you get like significantly better results. My next talk, which is going to be about like for reading groups, is going to be about optimizers in machine learning. A lot of them are actually based on BFGS and some ideas of BFGS. For example, Sophia, they're trying to use a single vector as an approximate of the Hessian, because having any information about the Hessian is infinitely better than not having it. Well, not infinitely, but it's quadratic versus linear convergence. So, that's great. So quasi-Newton is amazing. It's used a lot for every sort of, if you have a convex problem, you can usually use Newton's method or BFGS if you have too many variables. If you have a lot of variables, like millions, you'll actually want to look at a modified version of BFGS called LBFGS, which works really well with sparse values. But if you have billions, then you really just have to do gradient descent because you'll just store too many numbers for it to be to work outright. Yes.
So, just to clear up the confusion, I thought LBFGS was the like method of using quasi-Newton, equations to.
LBFGS is a slightly modified version of BFGS, which uses less memory.
I thought like BFGS was actually using the machine, and LBFGS was just using the quasi.
No, both of them are quasi-Newton methods. LBFGS is just a variant of BFGS. The person whose textbooks I took a lot of this from is Nusedal, who is the author of the LBFGS algorithm. All right. Any questions? No? Yes, maybe? Yes.
You made a point about how quadratics are a lot better than linear, about cubes. It's just too much functionality.
Right, I did mention I was going to talk about cubics. So cubics are, so you already realized how like the second degree was very hard to compute. Cubic is going to be an extra order of magnitude in computation, right? Because your Hessian, like you move from a Hessian to like a 3D matrix, so like a tensor. And so now you'll have to do n cube computation. And like, I'm not even sure how I would handle like the inverse of this, right? And like the inverse of a cube like matrix or like a cube tensor already becomes a lot more complicated to handle. Do you really want to go through that, or like that's going to be like the easy answer? The more complex answer is like, I mean, that's already like easy answer is complicated enough, but like BFGS already gets you like really good and very quick answers. Like quadratic convergence is plenty fast enough for like basically every application. Like you get less and less information the more terms you add to your Taylor series, right? So like there's very little point afterwards to like add third or fourth degree optimization. Does that make sense? Like, did that answer your question? Yeah. And yes,
Go back to slide 20.
slide 20.
Yeah.
Yes, this.
Could you explain why you introduced the UK and the GK?
Yes. Always, as I said before, like there's a BK right here. Just before those. So we want to see how we can update B of K into BK plus 1, right? We want to make minimal changes to BK to go from BK to BK plus 1. And we're going to change only 2 ranks of BK. And so to change 2 ranks, we're going to add 2 individual matrices that are each of rank 1. So how do we create rank 1 matrices? Well, you just use an outer product. And you multiply it by a scalar, just so you can have any scalar. And so this is how you get BK plus AUU plus BVV. And then like this is when you eventually get to choose your U and your V's as like natural choices. And that's where you come from. Why do you not do it with just one of them? It's because of degrees of freedom is one reason, but also you can't actually, where is it? You actually can't show positive definiteness with only one update. Like and so positive definiteness allows you to guarantee minimums. So if you don't have it, you can't use it. So that's the reasoning why you do with 2 of them and not just one. Does that make sense?
Yeah.
Yeah, perfect. Any other questions? I want to make sure everybody understands like what BFGS is. Good. Perfect. Then I'm done. Like, yeah, those are my sources, like 3 sources, but pulled a lot from the first one, which is a blog to help me like guide this. Second one is the actual like book where I pulled a lot of this from. And the third one is just the CS 520 class at Purdue, which I took last semester, which taught this. So